this video, and I'm probably going to break it up into multiple videos. So these videos are going to go over the solutions to the practice test for our Unit 3. So I would advise you to kind of do the whole practice test kind of as best you can, like an actual test. All right, try not to use your notes, try not to use the videos yet. All right, go through and kind of see what you think you know, what you don't know. And then come back and watch these videos, kind of compare the answers to what I get, see what mistakes you might be making, and then you kind of reach out in tutorial or something before our test. All right, and then when we take the real test, hopefully you already have an idea of how to do some of these problems. All right, so the first learning objective is all about defining average and instantaneous rate of change. All right, so the first question is literally just telling you to find the average rate of change. All right, so the average rate of change, remember all these rates of change are similar to slopes. So really you're just thinking about the slope formula. But we're doing it when x is 5 and 2. Well, if those are our x values, how do we figure out the y values? The y values come from when we plug those x values into our function. All right, so when I plug in 5 into my function, I get 15. That's the y value that goes with 5. And I do the same thing with 2. Minus 2. Oops, I put 4 squared instead of 2 squared. So 2 squared minus 2 times 2 is 4 minus 4 is 0. So the y value that goes with 2 is 0. And now I simplify my expression to get 5. And so the right answer for the average rate of change of this function from 2 to 5 is 5. All right, so this one just has kind of a formula you have to remember, and then also how do you find these y values when you know the x values. All right, the following table gives selected values for the function s. Use these values to approximate the instantaneous rate of change at x equals 2. So this is just a kind of definition thing that the instantaneous rate of change is the average rate of change as points get closer. All right, so what you want to do is get your average rate of change, but pick points that are really close together or close to the value you care about. So there's actually two right ways you could do this problem. You could do the average rate of change from 2 and 1.99 because those are pretty close together. Or you could do the average rate of change from 2 and 0.01. All right, so either one of those average rate of change should give you the right answer. I'm just going to do the first one. So we would take the y values divided by the x values. All right, this is going to be 0.04 divided by 0.01. And I'm pretty sure I know what that answer is, but I'm just going to use the calculator to check. 0.04 0.01 is 4. All right, so my closest average rate of change I can find in the table tells me that the instantaneous rate of change should be 4. All right, so again, just pick the numbers that are closest. If you did the blue ones, 2 and 2.01, you get the same answer. All right, 3. Which of the following best describes the instantaneous rate of change of f of x at 4? All right, well, we have this definition for the instantaneous rate of change. All right, this is a little bit before we started doing all these derivative tricks and everything. All right, so this is our original definition for the instantaneous rate of change at x equals a. So we have 4, so this is going to be a 4 plus h and a 4. All right, so 4 plus h getting plugged into our function. You plug it in for the x's here. So we'd have 4 plus h cubed minus 5 times 4 plus h. All right, so this one is definitely not right. Neither is this one because it has a limit of x going to 4 instead of 0, so that one's out. All right, this one has 4 plus h cubed, just like it should be, minus 5 times 4 plus h. So that one looks right. This one has the 4 plus h cubed, but it has 5x here. You have to plug this 4 plus h into both. All right, it tells me c is going to be the right answer. All right, so that's just applying that formula correctly, plugging 4 plus h in for both x's, minus when I plug in 4 for both x's, and then the whole limit thing's correct. All right, so C is the right answer here. I use the limit definition, which I just wrote above, to find the instantaneous rate of change of this function at 1. So we know our limit definition. All right, 1 plus h minus f of 1 all over h. And again, it's just simplifying this limit, so I'm plugging in 1 plus h in for x, so it's really similar to the one just above. We just have to do a bit more work, minus when I plug in 1 into my function. All right, and the most important thing here is to remember to distribute and FOIL appropriately. So it's going to be 1 plus 2h plus h squared plus 3 plus 3h. And then 1 squared plus 3 is 4, so minus 4. And you know you've done this right when the terms that don't have an h in it cancel out. 1 plus 3 minus 4 cancel. I have 5h plus h squared over h. Allows me to factor out an h. Which means I can cancel that h, and as soon as you cancel that h on the bottom, you plug in h equals 0, and you get 5. So it's very, very rarely that I tell you to solve a problem in a specific way. This one, I do want you to solve it using the limit definition. But we could check our answer using what we learned towards the end of the unit, is that f prime of x, using the power rule, is 2x plus 3. And if I plug in 1, I'm going to get 2 plus 3 is 5. So I get the same answer. So that's one way you can just check yourself to make sure you didn't make a mistake along the way. All right, doing the power rule method is going to be a lot simpler, but not the way that I'm looking for in this specific problem. And the reason I'm doing that is because even on the AP exam, we'll have multiple shortcuts by then. They still expect you to know this limit definition. So I'm still just going to make you learn the limit definition for the test, because the AP exam is going to make you do it as well. All right, our next learning objective, all right, using derivative notation and kind of knowing what a derivative is. All right, but remember, derivative is the slope of the tangent line. So the equation for the tangent line to the graph at x equals 3 is given by this. Which of the following statements is true? Well, using what I just said, the slope of this line is 4. So the derivative at 3 should be equal to 4. And that's one of the things that's correct. The other ones have to do with the original function. So let's start with 2 first. With the tangent line at 3 touches the graph at 3. So at 3, I should be able to plug that into my value or my equation. So when I plug in 3 into my line, I get 18. But since that line is on the graph there, I also know in my original function, if I plug in 3, I get 18. So 2 is also right, because that tangent line is touching my graph at 3. And the last one's kind of a trick question, at least that's what the AP people are hoping, because if I plug in 0 into the same equation, I get 6. So it looks like if I plug in 0 into my original function, I should get 6. Remember, the tangent line only tells me what's happening at exactly that point. I can have my tangent line keep going this direction down to 6, and my function can go off in a different direction. So it only tells me the point on my original graph once at that exact value, but not what's going to happen at other values. So even though this is true, 0, 6 is on the graph of the line, well, that necessarily doesn't have to be on the graph of the function. So that one's not true. So 2 and 3, C is right. And so knowing that the tangent line, the slope is the derivative, a point on the tangent line at that x value is a point on your original graph, but that's all kind of 2 things that you can get from just the tangent line. All right, this one, we have our tangent line drawn at x equals 3. So this is our point at 3. We know what is the f prime of 3. And remember, f prime is the derivative. So the derivative at 3 is the slope of the tangent. And the slope is rise over run. So we have to go down 1 over 2 to get to that next nice point on our graph. Well, down 1 over 2 is negative 1/2. All right, for 7, we have our function. We know that f prime of 2 equals 11, so they're giving this information to kind of save us some time for the problem. All right, find the equation of the tangent line at x equals 2. So the tangent line we can make using point slope form. We know the slope is given by the derivative, so that's going to be an 11. The x value is 2. How do we figure out the y value? Well, the y value comes from the original function, so we're going to plug in 2 here. So f of 2 is 3 times 2 squared minus 2, which is 12 minus 2 is 10. So the y value at 2 of my original function is 10. And now I just need to solve for y. It's going to be 11x minus 12. Okay, there it is. I didn't think the answer was there for a second, but there it is. All right, so 11x minus 12. All right, so it just kind of saves you a step of actually having to find the derivative yourself that give you that, but then knowing how to find the tangent after that. And the short answer one is similar. It's just using tables of values instead of an original equation. We're going to find the tangent line at x equals 3. All right, so tangent lines we normally do using point slope form. Our point is going to come from our original graph at 3, which is going to be this box. When I plug in the x value 3, I get the y value 4. My slope is going to come from my derivative, which is that box. So I'm going to have y minus 4 equals 2 times x minus 3. So the slope comes from the right-hand column, the point comes from the left-hand column, and I want it in slope-intercept form, so I just have to do a bit of simplifying. You get y equals 2x minus 2 as your final answer. So really similar to the previous one, you just have to use the correct parts of that table in order to create your equation. Our next learning tip has to do with derivatives or estimating derivatives. All right, the first couple have to do with graphs, and then after that it's tables. All right, but if we're going to find f prime of 2, all right, we're looking at 2. And we're thinking about what the tangent line looks like. So the tangent line here is kind of going in this general direction. And it's just an estimate, so your line might not be exactly right. But one thing we do know is this line's going downward, so I can automatically cross out the positive answers. And then is it more likely to be -3 or -1/3? Well, -3 would say I'd go down 3 over 1 to get my next point, and it would be that line. -1/3 would say I'd go down 1 over 3, and it would be that line. And which one of those is more likely to be the exact tangent? Probably the blue line, -3. I guess -1/3 kind of cutting through the graph versus -3 kind of goes with the graph. Right? So the derivative at that is -3. The graph to the right represents the function x, which of the following must be true. And you see these are all saying the derivatives are bigger than 0, so basically they're positive. So let's look at the derivative is the slope of the tangent line. So we're looking at 1, 3, and 4. Again, they're just estimates, but the tangent line here is going to be about like that. Tangent line here is going to be about like that. And at 4, it's going to be about like that. Again, they're not exact, but all it matters is that at 1 and 4, those lines are going up to the right, which means their slope is positive, which means the derivative is positive. So 1 and at 4 should be positive slopes. At 3, the tangent line is definitely going downward, and that means that the slope is going to be negative. So the derivative is not going to be bigger than 0. So my answer should be 1 and 3. Let's see. Because those are the places where the tangent line is going upward. The following table gives selected values of the function f. Use these values to best approximate f prime of 4. This kind of uses our first learning objective, to approximate the derivative. We can use the average rate of change of values that are close to 4. And the values that are closest to 4 are 3 and 5. So to find the average rate of change there, I have y values on the top, x values on the bottom. That average rate of change is going to be the best approximation I can find using this limited amount of information. 4 plus 2 is 6. 5 minus 3 is 2. And 6 divided by 2 is 3. All right, so the best approximation I can do for f prime of 4 would be 3. And it might not be 3, but that's the best I can do with this table because those are the values closest to 4. All right, 12, you're creating your own graph. You want the derivative at -1 to be 1, and derivative at 2 to be -1. Right. There's a lot of ways you could do this graph, but I'm going to try to do it in the simplest way possible. Is that we know for a line, f prime of x is just equal to the slope of that line. So at -1, if I just have a line with slope 1, so -1's here, the line with slope 1 is going to look like this. All right. That line has slope 1, so the derivative at 1 will be that slope 1. At 2, I want a slope of -1, so I'm just going to have at 2, -1, that's a slope. And then I can just kind of have them meet somewhere in the middle. All right, there's not going to be a derivative at that cusp, but all that matters is at -1, that slope is 1. At +2, that slope is -1. All right, so that's the kind of the simplest graph you could do to make both those true. Again, you could do something crazy with curves and just making sure your tangent line is like that and your tangent line's like that or something, but that's going to be harder to approximate and get them exactly right. All right, so using straight lines is your best bet to make it as simple as possible.